In this video, we're going to be going over several examples of continuous functions as well as those with points of discontinuity. So the first function we're going to be looking at is the infamous sine x over x function. In particular, we're going to define f of x as sine x over x in the open interval negative 2 pi to positive 2 pi. Now, hopefully you remember that this function is undefined at x equals 0, but you probably remember from your study of limits that the limit is equal to 1. This is actually an example of a removable discontinuity. So why is it an example of a removable discontinuity? Well, there's a hole here at x equals 0, right? If we fill in this hole, then this discontinuous function becomes a continuous function. So what that means is we can redefine this function, or we could, there exists another function, capital F of x. That's going to be equal to sine x over x in this subinterval here, open interval negative 2 pi to 0, as well as this interval, open interval 0 to positive 2 pi. And it's going to be equal to 1 when x equals 0. So this new function is the same as the original function, the only difference being with this hole filled in. So this new function is indeed continuous at x equals 0. And again, graphically, that means that at x equals 0, you can draw the function, you can get to points on the function with adjacent x values without having to lift your pencil off the paper. And this function is actually continuous now wherever it's defined. So the original function had a removable discontinuity at x equals 0. Now let's say we're looking at the function g of x equals x cubed minus 6x squared plus 8x, and g of x is defined over the domain, over the open interval, 0 to 4. So the graph looks like this, and you can see that you can draw the entire function without lifting your pencil off the paper. So this function is continuous everywhere inside its domain. Now in this example, we'll be looking at a pretty interesting function here. H of x equals x minus int of x, defined in the open interval negative 3 to positive 3. Hopefully you remember that int of x is the greatest integer function. It's also called a floor function. So it takes whatever you plug in for x and spits out the largest integer equal to or smaller than x. So if you want to define, say, int of x for x equals 0.5, then you get 0, right? If you looked at x equals 1, int of x would spit out 1 because 1 is the biggest integer equal to or less than 1 itself. 1.5, if you plugged in 1.5 for x, int of x would spit out 1. If you plugged in any number between 1 and 2, really, exclusive of both, well, inclusive of 1, exclusive of 2, so any number from 1 all the way up to 1.99999 infinitely, int of x would spit out 1, but at 2 it would spit out 2. But here we have x minus int of x. So let's look at 0. Well, x is 0, but what's int of 0? Well, int of 0 is 0 too, right? Is 0 as well, I should say. What about at 0.5? Well, 0.5, at 0.5, x is 0.5 minus int of x. What's int of 0.5? Well, that's 0. 0.5 minus 0, that's 0.5. So it'll just spit out x. And really at any number up until x equals 1, so at 0.99999, x would be like 0.99999. int of x would still be 0 because 0 is the biggest integer equal to or smaller than 0.99999. So 0.99999 minus 0 is 0.99999. You'd get back x. But right at x equals 1, the function value will drop to 0. And why is that? Because at x equals 1, well, x is 1, and int of x is 1 as well. So 1 minus 1 is 0. And this pattern kind of continues on like so. And this is actually called the Sawtooth function because it kind of looks like a sawtooth, right? So this function is continuous at all points except at integers. And at each integers, it has a finite jump discontinuity. And this is a non-removable discontinuity because there is really no way to redefine the function at an integer to be able to draw the function without lifting your pencil off the paper at that particular integer. So, for example, at x equals 1, there's really no way to redefine h of x so that you can get from points just to the left of 1 through 1 to points just to the right of 1 without having to lift your pencil off the paper. Here we're looking at two functions. First function is f of x equals 3 to the x, and the second function is g of x equals 3 to the negative x. So both of these functions are actually continuous for all real numbers x. So f of x equals 3 to the x, it's just an exponential function with a base 3. So you plug in any x, regardless of what x you plug in, you will always get a meaningful value for 3 to the x. Let's say you plug in negative a million. Well, you'll get 1 over 3 to the million, and that'll be a very small positive fraction close to 0. And if you plugged in negative a million and 1, you'd get a slightly smaller fraction, a bit closer to 0. There is no problematic point in this function. So it's going to be continuous for all real numbers x. And this function here, g of x equals 3 to the negative x, well, whatever happened for a given value x in f of x equals 3 to the x is going to happen for that same value of negative x in g of x equals 3 to the negative x. So, let's say we plugged in negative x here into this equation. Well, whatever happened, so I don't know. Let's say we plugged in. Let's say we plugged in 100 here. Whatever. So we'll get 3 to the 100. So, but that same thing will happen here in g of x at 3 to the negative 100. And so hopefully you can see that these functions are essentially reflections of one another over the y-axis here. And they're actually reciprocals of one another as well. But yeah, so this function, regardless of what value of x you plug in, you will always get a meaningful value of g to the x. Let's say you plugged in a really big positive number for x, you will get a very small positive fraction very close to 0. You make that number of x a little bit bigger, you'll get a fraction slightly closer to 0. And by similar reasoning, any exponential growth curve of the form f of x equals a to the x, and here a is any number bigger than 1, it's going to essentially bear the same form as f of x equals 3 to the x. It may be steeper or less steep than f of x equals 3 to the x, depending on what the specific value of a is. And any exponential decay curve of the form a of x equals, or g of x equals a to the negative x for a greater than 1, it'll look basically kind of like this. It'll fall from left to right, and in an exponential fashion, and the specifics will depend upon the value of a. But again, you will not really get in either of these cases, your generic exponential growth curve or generic exponential decay curve, you will not get a value of x that poses a problem and makes the function discontinuous. So in general, both of these, so all exponential growth and decay functions, okay, growth are of the form f of x equals a to the x, a greater than 1. Decays of the form g of x equals a to the negative x, again, a greater than 1. So all exponential growth and decay functions are continuous for all real values of x. Okay, so in the next video, we'll take a look at a few more functions. We'll be looking at the graphs of some logarithmic, trigonometric, and rational functions, and comment on their continuity or lack thereof.